So welcome again. I'm Vineet Tirvati, fourth year med student, and today we're going to be talking a little bit more about Python intermediate Python and how we can use some of its more advanced features to try to help us do machine learning. And the machine learning we'll talk about is this idea of training and testing. And it's a very different approach to how you analyze data that actually makes machine learning a very, very powerful approach to find and test and validate patterns. So today's workshop 10-11, we're gonna have a broad overview of what data is. Bear with us. I think this is important stuff to reframe how we think about data, but we'll talk a little bit about data. We'll talk a little bit about the idea of inference and what inference means and why it guides everything that we do. Then we'll jump into coding up a simulated experiment and running through an example with diabetes specifically to talk a little bit about how training and testing can enable us to figure out how diabetes works. And then we'll actually go into examples with splitting our data set. And all of that will be done together. I'll put the link, so that link is there just for afterwards when all of y'all have access to the PowerPoint, but I'll put that link in the chat so we can actually sit with it and work with it. Okay, and I want to super stress here, feel free to interrupt at any point if you have questions. This is meant to be, I want to stress this is meant to be overwhelming a little bit, but questions and comments and discussion are the best way we can work through a little bit of these concepts. Feel free to chime in, feel free to interrupt whenever you want in terms of audio, video, or chat, but I prefer audio or video so we can actually discuss things as a group, because if you have a question, chances are other people have questions as well. So I want to stress that before we dive in, because we certainly are going to be diving in. Okay, so let's start. Data. Everyone loves data. What is data? We need to have a conception of what data is and how it relates to what we care about before we really do machine learning. That's something that we're seeing in the field a lot, where people don't ask a question about what the data they're actually working with is. How does it reflect the thing that they actually care about? And so this is a little picture, a little depiction of how data is kind of a different thing than the thing we actually care about. So in this example, we have our heart, and that heart is a pump, and it pumps things, blood in and it pumps blood out. A lot of important stuff happens in the middle there, but for now, we'll ignore that and think we care about the heart. We care about our patient's heart when they walk in, and we want to make sure that it's okay. And one way we can make sure it's okay is by measuring things from that heart. And that measurement gives us data. And data typically turns into something that's quantitative or quantifiable. So in this case, we can measure two things, blood pressure and heart rate. And those measurements give us data that reflects what the heart is doing, but importantly, is not exactly what the heart is doing. We cannot understand a patient's heart by just measuring their blood pressure and just measuring their heart rate. So that is a very, very, very important distinction between data and the thing that we care about, which in this case is the heart. That heart has something called a distribution, and that distribution tells us how different properties relate to each other. So it's still early in M1 year, but in cardiology, you'll learn that there's a very specific way your blood pressure and your heart rate relates to each other. You typically, when you have high blood pressure and that blood pressure starts failing because your heart starts failing, your heart rate changes in a very specific way so that your heart tries to keep things going. We don't have to worry about that. That's for cardiology. The main part here is there's this unique shape that the heart of all of our patients typically takes when they're healthy. And that shape looks like this, right? So when you have high blood pressure, you tend to have low heart rates and high heart rates. But when you have low blood pressure, you tend to have high heart rates. You don't tend to have low blood pressure and low heart rate. What that means is what we're looking at here is a pattern. This is a pattern that the heart does. And when we measure what the heart does, we typically get numbers associated with this pattern, high blood pressures and high heart rates. So far, so good? The key point here, I'm going to keep hammering it, it's going to be the same point, is that our data is not the thing that we care about. Our data reflects, it's a window into the thing we care about. And that's important in how we do machine learning. So data is measured from something we care about, in this case, patient's physiology, the patient's cardiophysiology specifically. And the physiology has a range of values, a distribution. The blood pressure has a range of values, and the heart rate has a range of values that depends on the blood pressure. That is physiology. That is some true understanding of what we're trying to get at, and data reflects it, but data isn't equal to it. And finally, and what I just said, distribution reflects physiologic relationships we care about. And you'll notice the text pretty much just recapitulates what we talk about in these slides. Okay, so what is a measurement? Why is measurement important to actually spend some time with? Measurement is this idea of a perfect picture of a sunny day, which we are not having in Atlanta today, but a sunny day at a lake. And as we move to the left, we get this pixelation. That pixelation is maybe not a great camera. Maybe it's an old school camera, a flip phone camera that doesn't measure that scene as well as we want it to. That is the imperfection of measurement. We'll have a scene that we can see beautifully, and we'll try to take a picture of it. And in that measurement process, whatever picture we get isn't a perfect depiction of what we actually care about, which is the scene that we're looking at. And that takes a lot of different forms. But what that looks like in our patient is when we measure from the heart, when we try to get a blood pressure or a heart rate, if you position the arm poorly, if the position of the arm is above the head or way, way, way below the heart, you actually introduce something called noise, or a little fuzziness or a little wiggle room in your measurement of what the heart's doing. And so what you measure for the blood pressure and what you measure for the heart rate is actually not a reflection of just the heart. It's also a reflection of these other things, these other artifacts, these other noise sources that come in and screw up your measurement. And you can't ever see the heart directly, no matter, even with the CT and MRI, you're measuring parts of the heart and they always miss a little piece of it. But they always reflect a little bit of the distribution that you care about or the physiology you care about, but they introduce this noise into the picture. And a lot of our job in statistics, in data science, is figuring out how much noise is there in our data and how do we undo that noise so that we can actually study the data and get a good reflection of what the heart's doing, not a reflection of what your arm is doing. And measurements are always noisy. It's a little bit like that picture we have up there of the nice, beautiful scene. On the left, we have a lot more noise, and on the right, we have signal. So data can always be broken up into signal, which by definition is physiology. We're saying we care about physiology. So the signal is the good stuff that we want to learn and we want to describe. And it has noise, which is everything else, the things we don't care about. What are statistics? So statistics are our way to do inference. Inference is the almost reverse of measurement. Inference is how you go from the data that you've collected to the best picture of what the heart is doing that you can possibly get. And we do this on a daily basis as physicians in training. We look at a patient's lab values or we look at their blood pressure and we make an inference as to how healthy they are, or are they crashing? Are they in shock? Shock being when your heart can't pump enough blood to your body. So inference is our ability to go from data to whatever that true thing happening in your patient is. And one important way we do this is statistics. So what's in red is statistics. One statistic is averaging. So if you just go to the blood pressure and take the average of the blood pressure over a day, you'll have an idea of what the patient looks like. But that average also misses a lot of things. For example, if you just take the average blood pressure over the day, you miss the variability in that blood pressure over the day. And that variability might be telling you a lot about how healthy the patient is, because the average may be just right. But if that patient's going hypertensive and hypotensive, up and down, then the average will be just fine. But their actual variance, their other statistic, is where the information is, and you're completely missing it, and you're doing your inference imperfectly. And so measurement, our goal to go from measurement to physiology is inference. And sorry, so let me rephrase that. Our process of going from data to physiology is inference, and measurement is the process of us getting our data. All these things are very separate, and they're separate because each piece has a different thing that it adds to our process. And statistics are the calculations you do on your data to try to infer what's happening physiologically from your data, okay? And the last little bit, Python and machine learning are just glorified ways of us designing our own statistics. We may not care just about the average of our data. We may actually care about this other higher pattern, this other property that machine learning does a really good job of getting at. Python plus ML lets us design our own statistics and actually implement our own statistics on our data, okay? So I'll pause there. That was a lot. It's definitional. So this isn't something, you know, this isn't med school where we can't present something as truth and then say, go with it. This is one definition of it. And it's a definition that I and others have found useful in engineering, where if you split up this process of inference from your measurement just right, you can actually do a lot more important things in very, very messy, noisy situations. That's all the theory we'll talk about today, but we'll actually use what we just talked about in trying to use machine learning style approaches to inference versus the traditional way we do inference. Is there any questions so far? There's a lot I threw out at folks, so hopefully there's questions. Hopefully there's a discussion point. Does anyone agree, disagree? Does anyone have anything that wasn't clear? Please chime in, because otherwise I'm going to assume all of that was crystal clear and we're going to dive in. Was it crystal clear? Interesting. Okay, I guess it was crystal clear. Okay, so let's get to something a little bit more practical. And this practical portion of it is splitting your data. And one way we can split our data is something called training set and testing set, or train test. The best way to understand training set and testing set is to understand what we typically do, what we're typically taught is the way to do science and is the way to do something like EBM. The typical way, the way we're taught, is you design a very good experiment. You measure your data from that experiment. You do a bunch of stats on that data. You come up with things like means and t-tests and p-values, and then you publish it and you say, this is how our data looked after we collected our full data set in our experiment. And then once you publish it, someone else, maybe you, makes a second experiment. So you have a whole new set of patients and you design a new experiment to validate what the previous study just showed. Is that actually the mean? Is that actually the average effect of the drug that we just tried out? So you run a whole second experiment, you collect a new data set, you do some statistics on it, and you ask, is the mean I got in the second experiment the same as the mean I got in the previous experiment? This is typically called replication. And this is the way we're taught is science. So you do a solid experiment, get your data, analyze your full data set, and then let someone else do a second experiment, a third experiment, a fourth experiment, all building up to the idea that, yeah, that is the relationship that we found in our experiment. Now, what we're doing with training and testing is a little bit different. And it's a little bit different, but it's a bit more powerful. Why that is because you'll set up an experiment, you'll measure your data, but then what you'll do is you'll take your data and you'll split it up into a training set and a testing set. What that means is you're going to use machine learning to learn patterns or statistics. They're kind of the same thing in this discussion. You're going to learn some stats, you're going to learn some patterns in your training set, and then you're going to see how well that pattern predicts in your testing set. And the important part here is you split your data so that they're not overlapping. You take half your data, you put it over here in a different room, and you learn your pattern in what data set you have in your hand, which is your training set data, and you learn the pattern. And then you go ahead and you take only that pattern. You don't take any of the training set data, but you take that pattern over to your other room where your testing set is, where the data that you never saw before is, and you see how well that pattern actually does in predicting properties about your testing set. So with some caveats that we'll get to months from now, the only reason that pattern should actually do a good job of predicting in your testing set is if you learned the distribution that generated your training set. everything else, all the noise, all the sort of little bits that come in and influence your physiology, your signal, should kind of average out and may not be incorporated in your pattern. There's a lot of caveats to that, but the core piece of this is that pattern is what you're kind of learning in your training set, and it's the only thing you're taking over to your testing set. Imagine an extreme version of this. Imagine an extreme version of this where you split your training set and your testing set, but they're completely overlapping. You actually have a training set that is your testing set. So you'll learn something in your training set, and then you'll test it and see if it applies to your testing set, which is the exact same set. You'll achieve 100%. Your p-value will be 0. And sadly, people have published things like this, where they learn a pattern from their data set, and then they see how well that pattern applies to the exact same set they learned from. It can only be 100% if you do it right. So the extreme of training and testing is kind of the old school. What we do is just calculate the mean and then assume that that mean tells you something meaningful, and then let the next person see if that applies. In machine learning, we have the opportunity and ability to split our data, learn complex patterns, and then publish that pattern and let someone else do a replication, sure, but in a certain way, what we just learned was, yeah, actually this pattern does apply in general, because we split our data and are almost doing simulated 2 separate experiments. That testing set, in a way, is a simulated experiment too. But it's a really useful experiment too, because you did it, you know the methods, and the methods are the exact same if you design stuff right. The methods to generate your testing set are the exact same as the methods used to generate your training set. That's a powerful, powerful approach. The text only reflects kind of what we've been talking about. I do want to pause here, because the next step, we start getting into code and we start diving into a little bit more of how do we actually do this in practice? What does this look like in practice? I do want to pause and have a little bit of a discussion at this point. How is this different? Can someone explain to me why training and testing is so different from the old school approach? What does it maybe let us do in machine learning? And importantly, if y'all were there at the very first session of the semester, where we were doing things with dogs and we were doing things with, I think there was a baby involved, and then I think we did faces and fruits and stuff. Can someone explain to me maybe how that was related to training and testing? Cedric, I'm going to put you on the spot.
Oh, okay.
I'm not going to put any other people on the spot just because I know Cedric.
Right. Yeah. So we did have, like, we had a set that we had set aside to actually train our model with to teach it. I believe the one we committed to was like different, whether it was a malignant skin disease versus something else. I don't remember. But we had a set of data set aside for that, and then we took another portion of our data and used that to test whether our model actually learned to do it without using the same pictures that we used for testing, for learning, sorry.
Yep, that's what we did. We had one group of pictures that we know kind of belonged to melanoma. I think it was melanoma. And we had one group of pictures that we know was associated with not melanoma, or something we call healthy. Those aren't necessarily the same thing, but we considered it healthy. There were issues with that, and that's actually this approach to thinking about training and testing and inference makes bias a lot clearer. You can actually quantify bias a lot more formally. And so we discussed bias in that data set, but in that data set, given what data we had, we could split those two out. We let the algorithm learn whatever it learned. We actually don't know. I don't think we analyzed what it learned, but it was kind of hidden from us what it found to be useful. And then we tested it out in a different data set that it did not see ever before, and we saw how well it performed. And typically, it doesn't perform 100% because there's always a little bit of variability. But that testing set kind of gave us an idea of, yeah, we did learn something potentially meaningful. Now, there were limitations in what we learned. We talked about those, and we'll talk about them more when we talk about bias in machine learning in a later workshop. But that's exactly what we did there. We used that approach, which was almost like a second experiment, but wasn't actually a second experiment. Now, that's an important thing to keep in mind, because what we did there in that first session was a lot more complicated, because an image is very complicated. There's a lot of pixels there, there's a lot of numbers there, there's a lot of relationships there that we can see, but also that algorithm could kind of see. The example we're going to do today is not that complicated. It's a lot more straightforward. There's really only two variables, and we see multiple patients with those two variables. But I want to ahead of time stress that this general approach does a really, really good job. No matter how big your data set is, if that makes any sense. You can have a very big data set. You can have a lot of complex things that you're looking for in that data. But if you split things up into training and testing, there's no limitation necessarily inside there that requires you to have these massive sample sizes. If your signal is large enough, you don't necessarily need massive sample sizes. The old school way of doing it, where we do a very careful, clean experiment, relies on large sample sizes. It kind of has to have large sample sizes so that when you calculate the mean, you're calculating something meaningful. And then you test it out in the next round. So that piece I want to stress, because we're going to be doing some very simple things, mostly because we also have a goal of learning Python, and we have a goal of learning some of the basics of data science and machine learning. There isn't necessarily anything limiting you from extrapolating this to very large data sets. And hopefully you'll see that by taking whatever you learn here today and going to the examples that people already have out there. You'll see that the code surprisingly looks almost very similar, almost identical, because your data is in a single variable, and your training and testing method, or your training and testing function, splits it without any care for how many columns or rows that data has. Okay. All right. Any other points, any other discussion points, any other questions? Hopefully I didn't overcomplicate that or undercomplicate it, and it was fairly straightforward. But we are starting to take a step back from EBM and some of the stuff that maybe y'all are learning in the med school. Okay. All right. So that's that. The next thing we do, I don't think y'all can see that piece. Let's do this real quick. All right. Okay, everyone can see that? Everyone can see that, okay. I can't see everyone's thumbs up or head nodding, but I assume if you can't see it, you'll chime in with your mic. Good. All right, so I'm gonna send you a link to this. I would ask that y'all copy, paste. We'll spend a second doing this properly, but copy paste the copy the notebook. Oh, shoot, I am confusing myself with the two screens right now. Okay. I'm going to put the link in the chat. Okay, everyone sees that link in the chat?
Yep.
Good. Okay. So if you click on that link, and this is going to be a little bit of learning on my end too. If you click on that link, you should open up the notebook. Everyone, hopefully give me a nod if you can open up the notebook. I would highly suggest you open up the notebook. You can kind of follow along without being interactive, but that kind of defeats the point of the workshop. So if everyone can open it and then start telling me if they can edit it. Can anyone edit that notebook?
Wait, sorry, you want us to make a copy and then edit the copy, right?
Yeah.
Okay.
My guess is everyone should say, no, I can't edit that workshop or that notebook. And then we can go in and we can actually copy it into a separate one. And I realize every time I do a share screen, it screws up your workflow and makes full screen. So I apologize for that too. All right. Everyone opens up the notebook. One thing I would suggest, and this should work, so if you click Save a Copy in Drive, if you go ahead and click that, you should see a new tab pop up. You should see the top say Copy of MedML, test train walkthrough. Everyone sees that? Now in that new tab, do you have the ability to edit?
I do.
You do? Good. Okay. Perfect.
I don't think I can edit, or at least I don't know how to edit.
Sure. It says copy of MedML on the top.
Yeah, let me try again. Yeah, it says copy, but it's not letting me do anything.
So if you, so if you double click here, you see this pop up like this?
Yeah.
Good. So you do have the ability to edit. I'm pretty sure. And if you scroll down and you go down to the Let's Code part, can you type in Let's Code?
I think what's happening is like the top is you can't edit, but the code itself we can edit.
Okay. So so ignore what I said before with the top part. If you type in Let's Code into that box and press Run next to it, you should have an error pop up. That's a sign that we're on a good track. Everyone on the same page? Who said earlier, who just spoke, sorry, I should learn names also. Who just spoke about not being able to edit? Were you able to do this code part?
Yeah, that was me. I think I can do it. I'm trying to find where it is.
No worries.
It will let me type now. So
It will?
yeah.
Good. So if you type Let's Code, it should give a screen something like this. And I realize it might be difficult to have both my screen up and your workbook up. If that becomes really, really cumbersome, just let me know.
Just when I made a copy, the two cells under setup opened up, those can just be ignored. You can hide those.
Yeah. So if you click the arrow button, you can just collapse things that you think look overwhelming. Feel free to. I should put in a feature request for Google to maintain those collapses. Okay. To move things along, I assume everyone's typed in Let's Code and it threw this syntax error. Everyone know why it threw a syntax error? It's not code.
It's not real code. Yeah.
It's not real code. So let's make this real code real quick, just so we review what we talked about last time when Serenity gave us a Python overview. If we put print in front of that, put parentheses, put a quotation mark, put another quotation mark at the very end, close the parentheses. If we type, essentially giving Python the instruction of, go ahead and print this out to your screen. What should I print out? I should print out Let's Code. And I press play, we should see Let's Code. Everyone on the same page? Cool, okay. The next little bit is gonna be really fun. It's also potentially gonna be overwhelming to folks. Don't worry, that's completely normal. The goal of this section, what we're about to do, is to get you comfortable with some of the more advanced stuff that we talked about in the last Python session, and also start pushing you forward a little bit more to think a little bit more about intermediate Python and how we can use it to actually start splitting data sets and actually analyzing data sets. If you'll notice, below, there's a lot of other code going on. This code depends on what we're about to do and put into this Let's Code block, okay? So what we're going to do is build up into the rest of the code. And we're going to try to do this in the next 20 minutes. My suspicion is we'll get halfway through there and then we'll quickly show what happens in the rest of the blocks in the diabetes example. And then hopefully you'll feel comfortable enough with the diabetes example to work with it, because it actually has interactive components with it. It actually has sliders and text boxes that you can work with to see how training set and testing set work with each other, okay? So it'll seem like we're taking a lot of time with Let's Code, and we won't be spending much time with diabetes example, but the goal of that is to enable you to work with those examples after the fact. And the primary focus of this part is Python. So we're trying to be ambitious, but let's try it, okay? All right. So go ahead and blank that out from before and do me a favor and go up to runtime and click restart and run all. So when you do that, it tells Python to close itself, remove everything it knows about, remove all the stuff in its little playground, and just rerun this whole notebook again. And when it does that, you'll come back up to Let's Code. It'll be a blank box, and there'll be an error after that. That error is good because that error tells us name experiment is not defined. That code needs us to code up an experiment, a simulated experiment, before it can do anything that it needs to do. And that's what we're going to do for the next 20 minutes. And I'm going to keep saying it. If something is unclear or if something doesn't follow, feel free to interrupt me, especially with the coding portion of it, because it's really easy and really dangerous to just kind of leave folks behind as we're doing the coding part. All right. So I'm in a strange boat where everyone can see my screen still, correct? I'll assume that's a yes.
Yes, we can see your screen.
Good, good. All right. So I'm going to open up, obviously I have a notebook where the full code is already done. That way we can make sure we don't run into a lot of errors as we're coding. And you'll have access to the full code as well as this kind of more interactive bit. All right. First things first, let's talk a little bit about comments and what comments are. Comments are when you do a hashtag and you can type whatever you want. So if I type Let's Code here, we're going to code up an experiment. And I run that, it'll run without any issue because that's a comment. It's meant for the reader, it's meant for other coders. The machine doesn't care about it at all. So let's go ahead and do that. And if you remember from last time, one of the last things Serenity talked about was functions and methods. The functions and methods are absolutely important for us to be able to do anything in coding, because what they do is they package up instructions that we can keep using again and again and again later after the fact for however long we want. That way we don't have to keep defining some basic instructions. And when I say define experiment, I'm saying anytime you see experiment, do this set of instructions, okay? And these functions need a little bit of information most of the time about, well, yeah, I'll do these instructions, but I need some information from you so I can do these instructions properly. And so what we'll do here is we'll do n. Every experiment has an n, it has a sample size. So we pass to the experiment a sample size. We also pass to the experiment a group. And for this, we'll pass it a group called healthy by default. If you have a method and you have this argument, they're called arguments. We're defining the arguments. If you have an argument that says group is healthy, it says ask the user if they want a group, but if they don't tell you a group, go ahead and assume it's healthy. It's a default. So if I run an experiment and I say run an experiment with 50 patients and the group says, and I don't say anything about the group, it'll run the healthy group. Noise is going to be what we talked about a little bit earlier. where that noise comes in and messes up our measurements. And then finally, we'll say plot false. So when we run this experiment, sometimes we want to plot, sometimes we don't want to plot. For example, if we're running 100 experiments, we don't want to plot each and every experiment. That'll actually slow down our entire machine. So when we do one experiment, we might want to plot. Is everyone following so far? Because I am kind of going a little bit slower, but you'll start seeing it ramp up pretty quickly. Everyone following along? If you ran this right now, it would do nothing. It would actually throw an error. One way to prevent it from running an error is to type def. So we just defined a method called experiment, and we'll just say pass. And if you run this, you should have no errors, and you should actually have nothing pop up. Everyone on the same page? Good. All right, so, but we obviously want to do something more than just pass. When we call experiment, we want to actually do something. So the first thing we care about is the relationship. And so this is where we come in and we kind of know the truth. This is a simulated experiment. So the data that this experiment is generating needs to come from something we know. That physiology or distribution, we've already defined up in setup. We hit it, but that truth is there, and the experiment kind of goes in, sees what that relationship is, and uses that relationship to generate its data. So what I do here is I go to the true slopes, the true thing that we defined up in setup, and I say, go to that variable and call in the group, okay? Whatever group we defined in our experiment, we wanna go ahead and find that slope and run it, and actually store it in a variable called relationship. What we'll see is that this simulated experiment is actually about diabetes, and it's about how do we relate the amount of glucose you just ate to the blood sugar you measure in the patient. So we're going to do glucose eaten. It's a set of numbers from 0 to 100 spaced in 5 increments, spaced over 5 pieces. So what this actually means is you'll do 0, you'll do 20, you'll do 40, you'll do 60, you'll do 100, 80, you'll do 100. You'll take your 0 to 100 range and you'll split it up into 5. We talked about this last time in Python, but it never hurts to really recall what that means. And what we have on the other side is, this is called a list. And that list has nothing in it. And we're going to make n numbers of none, okay? This is just getting us set up for the simulated experiment. This is just going to get us set up to actually have a relationship of blood glucose based off of what we had with glucose eaten. The next thing we do is going to be a loop. And what we just did is set up our true relationship and the variables that we're going to be returning from the method. The method, when we run an experiment, at the output, we want some data. We want dependent variables and independent variables. So now we're going to go into each patient and define for them the actual value that we get from their experiment. So we'll actually output, this is going to be our dependent variable, blood glucose for that patient is equal to np.random.normal. This is going to look intimidating, but what this tells us is this is a Gaussian distribution. It goes to NumPy, which is a library that we imported up in under the hood. It's going to go say, make me a whole bunch of numbers that are distributed like a normal distribution. Great. Well, where should the center of that be? Where should the mean of that distribution be? Well, because we're doing an experiment and we know what actually is happening, we want it to be whatever your glucose eaten is, whatever the value here in our independent variable is, times the relationship that we defined in under the hood. The relationship that we actually care about, but in our simulated experiment, we defined. And then the last part of it is, we have a normal distribution has a mean, which is the signal. This is what we care about. I care about the relationship between glucose eaten and the blood glucose. And it has noise. This is the variance that comes in and kind of messes things up a little bit. And then that's honestly, that little loop is the experiment. That experiment goes in and generates the data from each patient. So it's okay if this is overwhelming right now, but just realize when you come back, hopefully you'll come back and double back, and we'll be stressing this again and again at different workshops. That loop is so important for us to actually fill in data. And those two lines do a lot of work for us, no matter how big N is. N can be 1,000,000. If we run this, you'll generate 1,000,000 blood glucoses from 1,000,000 glucosedins. And they'll all have different noise, they'll all have different problems associated with it, but at the core of it, they'll all have the exact same relationship between glucosedin and blood glucose, which is kind of what we do in medicine and science. We assume there's a relationship in all of our patients, even though each one's a little bit different. Last thing, I won't belabor this too much, but we do an if. We do a quick check to see, do you want me to plot the data that I just generated or not? So if you do want us to plot it, then we'll have a separate method, a separate function that goes in and plots the data we just made. Okay? We haven't defined that method yet, and in the way that I practice this, we were going to go ahead and code that. We probably won't. I'll just go ahead and code it real quick. I'll copy paste from before. But what this is saying is there's a set of instructions we made to plot the data that we just had. I don't want to run through those instructions again. So instead, if you want me to plot it, I'll go to this other set of instructions called plot experiment and let that method plot your glucosedin and your blood glucose and the group that we're in. And finally, at the very end, we'll do something that looks a little bit trivial. We'll just go ahead and define a new variable called illness. Sorry, that was wrong. We'll define a new variable called illness, and we'll just copy paste whatever the group you asked the experiment to run, we'll put into the illness variable. And this last piece is new. So this piece, I don't believe we went over last time with Python, but every time you have a method, it can do a lot of instructions. But one of the most important things that a method can do is return something. And here we want to return the data we just made. And every time I call experiment, it's going to do all these instructions and then literally hand off to me the glucose eaten, the blood glucose, and the illness. Okay? So that right there is our experiment. And if we go ahead and that instruction is there. So if we go ahead and press play, we'll see nothing happen because all I did was tell the code how to make an experiment. I didn't tell it to run the experiment. That we'll do right now. We'll run an experiment. We'll run it with 100 patients. And I said patients because let's do here, we'll say diabetic. And then we'll do noise. Well, actually, noise, I like 200, so we don't actually have to define that. Plotting, we want it to be false. It already is, but because we haven't coded the plotting portion of it, we want to go ahead and double check that it's false. So I want to make sure it's false. I don't remember what the default was, so we'll make sure it's false. And when we press this and we press play, we just generated and simulated an experiment. Everyone see that? Everyone see that? Can I get some verbal? Awesome. Okay. So if you coded with me, then what you just did was make a data set that links glucose eaten to blood glucose with a relationship that called true slope. And if you care, and I think everyone should care, it's just the code may be a little bit overwhelming. If you go to setup and you go to the variable called true slopes, you'll see something which we'll do, but again, don't feel overwhelmed. It's maybe not even that overwhelming, but this is the variable right here, true slopes. This is kind of what we're defining to be true. In the real world, when we work with our patients, we don't know this. So we use science, but more and more we're using machine learning to figure out what these values are. And so the true slope If I pass it along diabetic, it gives me 10. If I pass it along healthy, it gives me 1. Okay? Let's take a look at what that looks like, but I wanted to show you this because it's a new data structure called a dictionary. We talked about arrays and we talked about lists last time, and what those are just what they sound like, lists of numbers. And I can go in and I can ask Python to tell me what the 7th number is. I can go to Python and say, go tell me what the 12th number is. Go tell me what the millionth number is. Just go in, tell me what that number that I tell you, just give me that number and we'll move on with our lives. What this is it's a dictionary. It kind of does the same thing, except it doesn't ask you to tell it which element number to do. Don't ask me for the 12th number. Don't ask me for the 1st number. Don't ask me for the 18th number. Ask me, do you want diabetic or do you want healthy? And when you pass along what that group is, it'll return to you that number associated with the group. Hopefully I'm not losing y'all here jumping back and forth, but let's go back and revisit this thing that all of us just coded right now. We didn't know what that data structure looked like. This is coding. We call and we refer to things that we may not know the insides of, but we should always go double check, but we don't have to double check in order to get it to work. We said the relationship that we care about, that this experiment probes, that this experiment studies, goes to true slopes and then finds whatever group we just passed it. So here we passed healthy. Down here we passed diabetic. So when we actually called this experiment, it returned to us a bunch of numbers that, if we're just looking at, are kind of gibberish. We don't really know what this is showing us. So I'm going to be really, really quick about this part. I'm going to copy and paste the actual plotting just for the sake of time. We're going to copy paste the actual plotting data set into this. And unfortunately, this doesn't propagate to y'all's notebook, but you can go ahead and you can copy paste this later. And I'll send you the link to the full workbook. But when we go ahead and we code up the plot experiment that this experiment depends on if we want to plot, and we set up a whole run the experiment block. We have 5 patients, we define 5 patients, and we set up an independent variable, which is going to be our glucose eaten. We're going to have a dependent variable for diabetic, and we're going to have illness label for diabetic. And we're going to run the experiment with the number of patients we just defined here with the group diabetic, and this time we're actually going to plot it. And so when we do this, let's see if it runs no problem. We see a plot of the numbers that we just saw earlier. Okay? Cool? Hopefully that kind of gets people a little bit excited. This integrates a lot of what we saw last week, last workshop with plotting, but it splits it out into different methods that we can call as we need them, and if we need them, if we don't need them. If I go down and I change plot to false, and I run this, we see nothing show up. Why do we see nothing show up? Because before, when we saw all that list of numbers, we pretty much ran the experiment without telling Python what to do with the outputs of that experiment. So if I delete this whole section right here with independent variable, dependent variable, and illness disease, if I just delete that and I run this, you'll see all those numbers pop up. Here, there's not many because we just had 5 patients. But when we run the experiment and the experiment returns to us our data, Python assumes we want to just show it to ourselves. So it just prints it out and we see it. That's not what we want to do. We actually want that data because we'll use it a little bit later. When we press play after defining those variables and saying those variables are equal to the experiment, Python says, okay, great. Whatever data the method returns, let's put it into these bins called independent variable, dependent variable for diabetes, and illness for diabetes. Okay? Awesome. Now, in the last 5 minutes, and this is pretty much how I timed it, in the last 5 minutes, what we're gonna do is I'm gonna show you this because I don't think you're gonna be able to run this without plot experiment, though actually you might be able to run it without plot experiment. Let's do that actually. Go ahead and press plot equals false. Everyone can, I don't think you have plot experiment, but you do have experiment. So if you have experiment, go ahead and type this bottom 2 lines just as we worked with them. So type in num patients. That's the number of patients we have that we want to simulate. And then in a second line, make these bins and then run the experiment for a diabetic patient and put plot equals false. Everyone on the same page there? So if we press play, if we actually go to the left and press play, it should run without any problem. We don't typically like to see that. I like to see this all ran fine. You're good to go. Well, it doesn't like apostrophes. So let's do print, this all ran fine. And if we press play and it says this all ran fine, we know that the experiment ran fine. We know that there's variables with our experimental data. And we're actually, at this point, should be good to go. Let's see if that's actually true. If we go up to runtime and click run all, with this new code that we just sat here and coded up, the rest of it should run fine. There's a chance it won't because it needs to plot. We'll see if that happens. Did it run okay for everybody? Or did it run with an error?
Seems to be okay on my end.
Okay. So I just reran this and notice that actually there is an error because the rest of the code does require plot experiment. Darn. That's the problem. I'm going to act like this was intended. That's the problem with defining methods and not having those methods, relying on methods, but not having those methods defined. So for the sake of the last 2 minutes of this, I'm going to copy and paste the full notebook here into the chat so that everyone has access to it. So let's copy this link. Did that copy? Okay. So let's go ahead and do this into the chat. So that right there is the full notebook. And I would encourage you all to go work with that notebook. I'm going to show you real quick what it looks like and why this is the approach that kind of inspired MedML in the first place. Because can everyone still sees my notebook?
Yes.
Good, okay. So if we go ahead and go to the full notebook, this has the code that we just sat with, and it has the code for the plotting of the experiment, which you can go in, you can look at. It doesn't actually have any new concepts necessarily if you watch the previous workshop. If we go here and just, why am I not able to run this? If we go ahead and we run all on this notebook, you should see something pop up with diabetes example. So your 2 best friends are going to be run all and restart and run all so that we can actually let the notebook populate everything properly. And down here is going to be our first little interactive component. Is there an error for anyone else? Ah, okay. That was my bad.
Yeah.
All right. I was getting ahead of myself there. If you delete that or if you refresh the notebook, Ariba, Do you have the notebook open?
I do, yes.
Okay. Can you tell me real quick if it updated with me deleting what I just did?
Let me refresh.
Yeah, I think everyone might need to refresh, so you can go up and do a hard refresh. I'll go ahead and I'll show y'all just for the sake of time. But if you refresh, it should have the updated bit. If it doesn't, try out your Python problem solving and delete whatever has an error and see if it runs. That's actually like 90% of programming. Oh, that's an error. Let's just remove it and act like it doesn't exist and see if things run. And we'll double back and see if things are fine. So real quick, the key parts of the rest of the notebook, the pieces that we aren't going to spend much time on today, and maybe not in the future, because there's a different set of notebooks where we dive into linear regression a lot more. But the key part here is you'll actually have interactive cells. And what that means is we're going to call the functions that we just made and let Python put these sliders for us that we can adjust. And live, you'll actually rerun the experiment with the number of patients that you set in the slider. So what we focus on with the last piece of this workshop, this notebook, is not Python, it's testing and training. So we'll double back and we'll see how what we just coded up goes into our ability to do training sets and testing sets. So up here, we actually generate our data set on the fly. So if we're doing a diabetic patient and we want 100 of them, here's our data. We have glucose eaten on the x-axis, and we have blood glucose measured on the y-axis, okay? Kind of makes sense for a diabetic patient. If they eat 80 grams of sugar, their blood sugar is going to skyrocket because they don't make the insulin to tell their blood to push the sugar out. But if we switch our group to a healthy group, we have 100 now healthy patients. This makes sense, right? A healthy person maybe eats 100 and it'll spike just when we measure it, but for the most part, it won't spike as much because they're making insulin to take account for that blood. So this first interactive component is really just about generating a data set, having a different number. Let's reduce the number of patients so our legend isn't so big. And when we generate a set with 20 patients, we can actually then adjust the noise. And you'll see what noise does. Go ahead and explore this on your own. But when you reduce noise to 0, it's a clean relationship. Every single patient follows the exact same line, and it follows the line with slope 10, because we defined it to be 10. Whatever your glucose eaten is, the blood glucose is 10 times that. That's what we defined in our experiment. Noise comes in and makes things a little fuzzy. And that noise can be anything. The noise can be maybe our measurements are off a little bit, because no measurement is perfect. That lab is great, but it's not perfect. Or this can actually be very individual variation. People kind of respond differently to whatever glucose they eat. So you'll see a little bit of variability, but for the most part, they all still follow that line until we get into really high noise, in which case this might actually be difficult to find out which line is actually the relationship between the two. And that's where linear regression comes in. And this is where our next interactive component comes in. I'm not going to spend too much time on this. I would encourage y'all to not spend too much time on this, because we're going to have a whole separate workshop on linear regression. But the whole point of this is, can I figure out the value that we set up in our under the hood section solely from the data? If you remember way in the beginning, that's what inference is. Inference is me trying to get at physiology solely from my data set, because I don't know what the physiology is. In this notebook, we know what physiology is because we simulated the experiment. But over here, we start splitting our data set, and we start seeing if we only use 5% of our data to figure out in blue what the relationship is in these diabetic patients, how far off am I from the orange line, which is the truth? That code goes in, finds the truth, and draws that dotted line, which we don't know. And if we try different trials of this, you can actually see that if I'm only using 5% of my data, that blue line is all over the place. It really, really depends on which 5% of the data I use. In EBM language, this is like a low sample size. Okay, so if we try different trials, we'll see that line move a lot. But all I'm showing in blue here is the training set. Let's also plot the testing set. This is the data that I'm not looking at whatsoever in fitting that blue line. And it's most of our data. So these are the red pluses. The red pluses are our testing set. So we can go, and we don't do this in this notebook, we'll do it in the linear regression workshop. We go and see how well that blue line explains and fits our red pluses that that blue line never saw. That tells us how good our model is. If we start increasing the train percent, so I actually want more blue dots to be used in finding my blue line, let's go up to 90. Let's do the other extreme. Let's do 95% of our data is used to train our model, and 5% of our data is pluses. Well, that's great, actually. If you look at this and we try different trials, you'll notice that blue line, you can barely tell the difference between that blue line and the orange line, because we have a large data set with respect to one number that we care about. This is why this is a very simple data set, and we can actually achieve really good accuracy in estimating the relationship that diabetic patients have without getting to 95. We actually could probably go down to 25% and adjust the trials and actually get a pretty decent blue line fit. So go ahead and play around with this. This code is fully visible to y'all, maybe too visible to y'all. And you might want to maybe just ignore the code for the sake of training and testing, to play around with these widgets, these sliders, to see how does training set, how does testing set, and importantly, noise. How does noise factor into all of this? Because when you set up an experiment up here with a certain noise, if you reduce the noise a lot and you rerun this code block uses the data set you just generated up top. And then it tries to do training and testing fit in the data set you just generated. So you'll notice here, if my train percent is really, really low, it doesn't really affect things because my noise is so low that I really don't need a lot of data to get a perfect line. So start playing around with that. Those two interactive code blocks are kind of capture training and testing in a nutshell with a very simple data set. In our linear regression workshop, and I'm wrapping up right now, in our linear regression workshop, we start getting into how do we do this with more than 2 variables? How do we do this when there's 5 variables, 10 variables, a million variables? A million variables is starting at the low end of deep learning. That's such a, it's such a, some of y'all will have a problem with that. But when we start making these really, really large variable sizes, if I want to see how each gene actually comes in and affects what the blood glucose is, we can't plot that easily, but we know there's relationships, and deep learning comes in, other machine learning approaches come in and help us find those relationships. Great. It is 2:09. Thank you so much for staying, all of y'all. Hopefully that was helpful. I want to, if you got to go, feel free to go. If you have any questions, if you have any discussion points, feel free to stay. I can stay. I don't want to speak for anyone else. Anyone who needs to hop off can hop off. You should have both of these notebooks, the links to them, and I will send out the PowerPoint and a survey. Please, please, please fill out the survey. We'll send that out later today. And so you should have everything you need to start playing around with testing and training. But if you have to head out, it was great to have you. Thank you so much for coming. If you want to stick around and chat a little bit or have any questions, I'm around.